Okay, I think I'll start, and hopefully we have more people joining in soon. So this is joint work with Moshe Babaioff and Noam Nisan. And it's about a very fundamental problem, how to sell multiple items. It's actually, the topic of this paper is actually an even more fundamental problem, how to sell just 2 items. And it's great when you're working about such a fundamental problem. It doesn't matter that it's completely irrelevant in practice. No applications. But yeah. So let me form. Since we're talking about fundamental problems, let me formalize a model. I think that's the next thing that comes up. So I want to talk about a single buyer with additive independent values from known prior. So there are 2 items, the apple and the orange. Moshe tried to convince me it's an orange, I'm not sure. And there are different distributions. We know the distributions for the value that the buyer has for each of the items. Okay? And the buyer is additive, so his value for the bundle is just the sum of the values for the apple and the value for the orange. And as is pretty standard, there are some things that we don't allow in our model. So we don't allow, the seller knows the buyer's the prior distribution over the valuations, but the seller doesn't know the actual value. So the mechanism has to be truthful or incentive compatible. It's also pretty standard to assume that we cannot force the buyer to pay too much. And those are pretty standard assumptions that may or may not be relevant in practice. For example, if you're selling German submarines, maybe you have some ways to force the seller to force the buyer to pay too much. But here's an assumption that's really even in practice, I think it holds almost always. So there are no lotteries, no quantum mechanisms, no funny anything. Okay? So instead of telling you what's not allowed, here's what is allowed. Mechanism is super simple. You're given distribution for the apple, you're given distribution for the orange, and you post 3 prices: the price for the apple, the price for the orange, and the price for both the apple and the orange. No questions so far, right? Okay. And what we're after is a characterization of the optimal prices. So specifically, the question is how to price the bundle of the apple and the orange. So there can be an additive pricing. So the price of the bundle is just the sum of the price of the apple and the price of the orange. There can be a submodular pricing. So I'm giving a discount if you're buying the bundle. And sometimes, maybe, we might want to charge a supermodular price. So you're actually charging more for buying the bundle. And the first issue with this supermodular pricing is something called false name proofness. And I don't want to formally define it, but what it means is that supermodular pricing is not false name proof. So if I price the bundle more than the price of the apple plus the price of the orange, then the buyer in practice often has ways to get around this pricing, right? He's going to send his friend to buy the orange for him, or just come to the store twice, etc. Okay. Another sort of related question is revenue-monotonicity. So what happens if I could replace my distribution over buyer values with buyers with higher valuation? Okay, so formally, I have a distribution that stochastically dominates the older distribution. And now we expect that the revenue will increase once I switch to the higher distribution. But it turns out that revenue is the mechanism is monotone, as in the revenue only increases if I increase the distribution. The menu is monotone if and only if the menu is either submodular or symmetric, and we'll see a proof later. Okay. So the main question we're after in this work is the optimal mechanism always submodular, or are there some instances where it's better to use the supermodular prices? Any guesses? Last chance to guess before I. No one. Okay. Wow. Okay. So no. I mean yes. It's no. It's never better to use supermodular prices. Submodular is always without loss of generality. And this is sort of what you expect, right? You never charge more for the bundle. You want to give a discount because that encourages the buyer to buy more, and that gives the seller an opportunity to make more revenue. So this is a less surprising result maybe, but it turns out this doesn't generalize in any way. So if you try to think about the proper generalizations for randomized mechanisms, for the correlated distributions, for more items, nothing works. So in hindsight, maybe it is surprising that it works for 2 items. Okay. Another way to, let me give you a visual way to look at this supermodular versus submodular. You can plot this, plot the menu and the prices in the following way. So this is just the axis, and we will have a finite plot, but the valuations can go to infinity. And this point corresponds to having value v1 for the apple and value v2 for the orange. And if I charge price p1 for the apple, this is a line of indifference. So to your right of this line, the seller wants to pay more, so the buyer wants to pay more, so the buyer will buy the apple. And to the left, the buyer will not buy the apple. And above this line, this is the price for the orange, and above this line, the buyer will buy the orange. And this is just the additive where it doesn't matter if you're buying the bundle or not. So if you use a supermodular pricing, so the bundle is more expensive, this upper right, this upper right region where the buyer is willing to buy the bundle becomes smaller, and now we have this line of indifference between the item 1 and item 2, where the buyer switches from item 1 to item 2. And one more of those pictures. This is what a submodular menu looks like. So now we gave a discount for the bundle, so this region where the buyer wants the bundle becomes bigger. And now there is a point of indifference when buying nothing jumping to buying the entire bundle. And just to warm up, to make sure you understand all the everything works. So this is the proof I promised from Hard and Rennie. The submodular menu is revenue-monotone. So the idea is just to look at the submodular menu and see what happens when the valuation increases. So if the buyer starts here and jumps to buying one item, the revenue only increases. And similarly, if he jumps to buying the bundle or jumps for buying just the orange to buying the bundle. But in a supermodular menu, if it's not symmetric, if the prices are different and P2 is bigger than P1, here the buyer is jumping for from buying the orange to buying the apple, yielding less revenue for the seller. Okay, ready for the main proof? Excited? Okay, so this is the formal statement. You have to be a little bit careful because I told you the optimum mechanism is submodular, but there might not be an optimal mechanism. So for every supermodular mechanism, there always also exists a submodular mechanism that attains as much revenue. Anyway, so the idea is to start with a supermodular mechanism and try to modify it into an additive mechanism without losing revenue. And there are two natural ways. So one thing you can do is you can decrease the price of the bundle to P1 plus P2. It's pretty straightforward. The other thing that's a little bit confusing is to increase the price of the cheaper item to make it additive again. I guess not super confusing. Okay. And this is this is a supermodular menu that we start with, and these are the revenues the buyer gets in each region. And here's what happens in the first option where we decrease the price of the bundle to make it additive. So this is what the buyer gets now, on the bundle the buyer loses X. X is the difference, how much we're far from additive. In this region, the buyer gains, the seller gains P2, because previously the buyer only bought the apple, now the buyer gets both. And this region, the seller gains P1. Okay. And similarly, we can ask what happens on the second alternative menu, where we increase the price of the item on the apple, the cheaper item. And we can look at the differences between the supermodular and the additive menu. And these are the numbers that we get. There's plus X, minus P1, whatever. And now let's add up everything. So it's this pretty picture. And in this strip, the change in revenue when switching from the supermodular menu to either of the additive menus is always non-negative, so we're always gaining. And the question was what happens to the other two strips. So we have this symmetry. There's a plus P1 minus X and minus P1 plus X. And this is a step where we have to use the fact that the valuations are independent. So the probability of the plus X versus the minus P1 is the same as the plus P1 versus the minus X. So one of those has to beat the supermodular menus. Okay, so this is the main result. Let me recap with a couple of open problems. So for two independent items, the optimal menu is submodular and therefore also revenue monotone. And we have this funny corollary that by some other results, this gives tight characterization of how much you can gain by giving any discount versus just selling separately. And like I mentioned, these similar results do not extend to 3 items, to randomized mechanisms, etc. But here's a nice open problem that I would love to know the answer for. So when I said it doesn't extend to 3 items, we have an example where the optimal menu is not submodular. And for 2 items, submodular and subadditive are the same. But for 3 items, we don't have an example, or for 3 or more items, we don't have an example where the optimal menu is not subadditive. And I don't know if it's because we couldn't find one or because it's It's always subadditive. And we have some other results in the paper. For example, if the distributions are symmetric, then you would hope that the optimal menu is symmetric, and this is indeed the case. But this, again, doesn't extend to randomized or to correlated distributions. For randomized mechanisms, it's easy to, everything becomes symmetric. Just flip probability 1/2. Yeah, I think that's it. Thank you.